Reading week. I'm sure you all had a better one than I did. So just to start out then, to remind you, or to tell you that tomorrow we're going to be in Arts Tower Lecture Theatre 4. So not Lecture Theatre 6, as we have been in the past, Lecture Theatre 4. Okay, and I'm going to finish today, hopefully, this chapter here on decision trees and the variants of the decision trees. And I want to have a feedback session on assignment 1. So I'll spend a bit of time tomorrow talking about assignment 1. We've not actually finished marking it quite yet. I think I've got 2 left out of the 102 or who handed it in. But we haven't done our check marking, we haven't done our scaling, so any marks which I might make available tomorrow are going to change a lot, so you shouldn't actually pay any attention really to them, I hope. So I'll talk a bit about what I think makes a good write-up of a project. There are all sorts of ways of writing these things up, but I'll tell you what I like to do. I guess I'm quite interested also in finding your feedback on the module. So this is the first year, of course, that the module is run. I think that it's probably more useful and more important to stress the lab sheets than the lectures, and I think maybe that means that I shouldn't really be doing any lecturing, but I should run some classes instead and do some video lectures or something. And anyway, you just think of ideas for how to improve this for future years. Okay. Let me know. Anyway, so before reading week, we were thinking about decision trees, and that's a kind of example that we've already seen. So this was the example of the Titanic data set, and every passenger is at our root node, and then we're choosing a question on one of the variables. So first of all, is the a passenger male or female? If it's a male, then they'll go down to node number 2, and if they're female, to node number 3 here. And it then turns out that statistically the best improvement in our overall prediction then comes from asking about the males. Are they aged at 7 or more? And asking about females, are they in class 3 or in a higher class? And then once you do that, we can maybe stop there, and every terminal node then has some prediction of whether or not a passenger died or survived. And the regression trees are very similar, except rather than predicting a class, we predict some value here, some numerical value of our output variable. Right. So that's where we were then before reading week. And we were about at ensemble methods, which is a collection of improvements to the basic idea of a tree. And these improvements are formed by merging several trees. Okay. So trees are very quick to produce, which means that we can take advantage of that and actually make up lots and lots of trees. And I use those ensembles or collections to make some overall prediction. So trees are very easy to interpret as well. And just to look at one variable, a male or female, and then work out the next most important variable, and so on. They're extremely popular in machine learning, but people now realise that ensemble methods and merging several of them is a great improvement. So one reason then is that trees are rather unstable, and you don't have to change your data set to that much. Sometimes to change your early split from one variable into another variable, and then your whole tree ends up being entirely different and being interpreted in an entirely different way. So individual trees, in fact, are not actually all that accurate. So we're going to explain now some ensemble methods that merge at several trees and to give us an overall prediction, which it turns out to be much better. Okay. So, well, why do we do that? I guess you've all heard of this wisdom of crowds thing, which tells you that averages for lots and lots of estimates of something are generally extremely accurate. It goes back to about the 1900, when Francis Galton, who was an early statistician, had this experience at a county fair. I know my children's school fair often has things like how many sweets are in the jar and so on, and this is an old version of the same thing. So everyone who attended was invited to predict the weight of an ox, and it turned out that the mean and the median were really, really good estimates. So some estimates were wildly overestimated, and others were wild underestimates, but eventually the overall average was just about right. And that's the kind of thing here that ensemble methods are going to try and exploit. In principle, you can use them with all sorts of other methods as well, but in practice, they're almost exclusively used with trees, partly because trees are extremely quick, and that makes it easy to make lots and lots of them. Okay. So we're bagging in the random forests, first of all then. These are rather similar ideas, but the random forest just has one extra enhancement over bagging. So first of all, bagging is an abbreviation for bootstrap aggregating. There it is. So a bootstrap sample was mentioned earlier. So it's one where we take extremely similar data sets to the original one, and we do that by sampling randomly from the original data set, but with a replacement. So if our original data set had 5 observations, 1, 2, 3, 4, 5, we might first of all randomly choose observation 2, then observation 4, then observation 1, say, and then we might choose observation 4 again, and then observation 1 again, maybe. So it's entirely possible that our observations are repeated. So like this, we can find lots and lots of similar data sets all the observations are very similar to the observations in the original data set. In fact, they're exactly the same. And on each one of these, we can model a tree, a decision tree, and then if we give ourselves a new piece of data, every model that we just invented is going to predict either a class in a classification problem, or a value in a regression problem. In the case of a regression problem, we just average them and find some bagged predicted response value. And in the case of a classification problem, we can find a bagged classifier by taking a majority vote. So if we had, say, 5 of our models predicted class 1 and only 2 predicted class 2, then it's sort of more likely to be class 1, right? Okay. So that's our majority vote classification method. So there we've got some bagging, and there's a slightly more formal way of writing it down. So here we're starting again with a data set with some feature variables, some input variables in a vector xi. So here xi is the a vector of feature variables in observation I, and it has an output, a response variable yi, which is either a class or a numerical value. And so then from x, we're going to find n the bootstrap training sets just by randomly sampling. And then for each one of our sets, xi are going to form a tree, and each of our trees then it's going to predict the value or class of a new piece of data, say fi of x, and then we can average them in a regression problem, or to take a majority vote in a classification problem. So that's the basic idea then for bagging. Okay, and there's a picture there that's maybe not all that informative, but the idea is that that from our original data set we're finding sort of n similar looking similar looking data sets. Each of those is going to give us a prediction for a new value of x, and then we merge them into some overall response. Okay. So, well, the random forest is just a version of this, but slightly enhanced. So there's a slight problem here in that, as everyone knows, if you've got n independent variables, each of which has got the variance at sigma squared, then the mean has a variance at sigma squared over n. But in fact, that's only valid if our samples are independent. And when you think about how bagging works, that's actually not all that likely. I mean, each of our original data sets is fairly similar. It's quite likely all of them are going to have their first split on exactly the same variable and to similar values, and quite often all the early splits are going to be the same. And that's going to lead to a correlation between our trees and eventually our predictions. So it's only true that the variance of the mean of n samples is sigma squared over n if all our samples are independent. And in fact, if they're exactly the same, for example, then the variance of the mean is just going to be sigma squared still, and they're not even sigma squared over n. So slightly more generally, and it's in the lecture notes, if you have, say, n samples, each of which are pairwise correlated with a positive correlation rho, then it turns out that the expected variance of the mean is actually rho plus 1 minus rho over n, all times at sigma squared. And we'd really like that variance to be more and more accurate. We'd like to be more confident that as n approached infinity, our variance was actually approaching 0, which is going to mean that we'd really like our rho to be very small and n to be very big. So even if we take more and more trees, if our value of rho is actually positive, then our final variance is always bounded below by rho sigma square. And that's not what we want, really. So random forests are a clever way to try and avoid this correlation. So the idea is at every stage, rather than thinking about each of the p variables and thinking about where we'll split on each of the p variables, we're going to choose a smaller subset, maybe of size, say the square root of p, or p over 3 or something. So at every split, we're going to choose a smaller sample, so a smaller random choice of variables where we might actually split. It speeds things up, of course, since we're only thinking about a smaller number of variables. It also increases the variability of the final trees and the variability of the final predictions. It's likely that every single tree that's formed in this way is actually worse than a reasonably good tree that we'd formed earlier. But nevertheless, since they're more and more variable, hopefully their average is a more and more accurate estimate of the right value. Now, apart from that, that's the only difference between random forests and bagging. So exactly the same. We just taken an average classification for a regression problem or a majority vote in a classification problem. Okay. as you'll see on the lab sheet at 6, all these things are in R and Python already. So, anyone started lab sheet 6 yet? Okay, well, plenty of time. Right. So it turns out that random forests in practice are a vast improvement on the bagging, and they generally work extremely well. It can happen though that if your classification only depends on a fairly small number of variables, that none of them are actually chosen in your random samples until maybe quite a long way down the tree. So sometimes it's not quite as good as other times. Okay. So there might be, for example, that there's a really important variable in the classification that hasn't appeared in any of your splits by the time that you're pruning your tree and they're not growing it anymore. Okay. Right. So with boosting then, this is an alternative way for using lots of trees, and in practice this works really well. So maybe some of you have heard of the machine learning competitions at Kaggle, Kaggle. So it's usually the case that the boosting does extremely well on the general classification problems. So for things like images, maybe neural networks are slightly better, but on the general problems, it's usually some variant of boosting that does extremely well. So Kaggle is a repository of machine learning competitions, data sets which are uploaded, and problems which are given out to maximize the success of prediction on some previously unseen testing data. So random forests work extremely well. They got by you randomly choosing lots of samples and then applying your model to each one and then merging them. So it's kind of like an electric circuit working in parallel, I guess. So with boosting works by changing your data set at every stage, and it changes it in such a way that it takes extra account of the things where the previous version did really badly. To the idea. I'm not sure I explained that especially well. So how does boosting really work then? We're going to think about a model. I'm going to work out to where it's going wrong and where it's not doing the right thing, and then sort of focus your data set on those observations. So I'll start by talking about adaptive boosting, which was invented around 1995 by Freund and Schapper. So we're going to look especially at a classification problem here. So in any model, we're going to work out which observations are incorrectly classified and then we'll weight those more highly, which makes them more likely to be chosen as inputs into the next data set. So they're more likely to appear more often in future data sets in your samples. Okay. So there's a kind of an attempt to make a similar looking picture. So here we might have a data set here and a model F1 which misclassifies that value and that value and that one, and then we increase the corresponding weights, which make it sort of more likely to be chosen next time. So, so for example, next time, so if we've got however many points we've got there, 5, 8, 13 points or something, we might now imagine that these points are going to be twice as likely to be chosen, or if you like, we've got 16 data points here with every point that was incorrectly worked on at first time is now appearing twice. Okay. Okay. And the next time there are going to be more things wrong. If the point there may be misclassified by each of the first two, and so it has an even higher weight. Or now other things might also be more highly weighted because a second model that got those wrong as well, and so on. And then each of those is giving us some a prediction, either a value or a class, and so then they're merged in a similar sort of way. It'll probably be some weighted average, because it's more likely that your later classifications are getting more things right. So it'll be some weighted the majority vote, or a weighted average where your later ones are the more highly weighted to give you your final prediction. And we'll see another method in a moment. So that's adaptive boosting, and I kind of explained that. So most often our trees are in fact not full decision trees, but so we often simply use a one-layer tree or a stump. Okay, so one root node and only one question. So stump. So it's a one-layer tree. Okay. Even so, it works really well. This is the slightly odd thing. So I think there's a to miss that out. It's stare here at our picture, because this is actually a nice example. It's one that I found online this morning. It's a better explanation than all the words in my notes. So here we're starting with a data set then, a D1. Okay, so we stare at that. So 5 of our entries are in the minus class and 5 in the plus class. So here we've got a bivariate set. So variable 1, say, going on the horizontal axis, and variable 2 on the vertical axis. And our first decision stump then is on the variable 2. and we're asking, is a variable 2 larger than a threshold or not? And let's make our threshold here. If it's larger than that value, we'll take it in the minus class, and if it's less than that, it'll be in the plus class. Okay. And you can see easily that the 3 things here are being misclassified. So that plus there and the 2 minuses there. Well, now we reweight our data set, and the observations that weren't right first time are now weighted more highly. So that's a larger plus than those, and those are larger minuses than the other one. Okay. And now we try and find our optimal stump again, and we're really penalising getting these things wrong even more because they're larger. Okay, so it might be that's our best choice now with our new weighting. And you can see indeed that none of the larger ones are wrong, and in fact it turns out here that none of the pluses are wrong either, but 3 of the minuses are wrong. And so we use those and to make the wrong minuses slightly bigger, and now all our minuses have been wrong once, and that plus has been wrong once. And now again we find a decision stump on the 1 variable, which here again is going to be our first variable, and ask, is our variable 1 larger than that threshold there, or is it less than that one? And there's a split there that gets all of our larger things right. So all the things that have been wrong are now right. I mean, other things are also wrong, but let's not worry about that because they're not as highly weighted. Okay. Okay. And then we merge those, and here we're taking a majority vote. That the region here in the bottom right has always been a plus region. These parts here, there and there, have been classified as a plus on 2 of our 3 models. The top left there has been minus in all 3. And the 2 rectangles here have been minus in 2 of the 3, and now you can see that in fact we've got all our 10 observations are now are correctly classified. So it's a very simple idea. It's rather amazing that it was only in 1995 that this was first published, but it's really the mathematical theory of this that was first written down then. Right. Okay. So there we go. So here's a slightly more formal thing, and here's a mathematical explanation of exactly how this works. It's not really necessary to understand those. Just stare at your picture there and to really work out how it works. And that's exactly what's done in R and Python, how it's programmed, and there's the formal algorithm. So here we're starting off by weighting all our observations equally, and then we're going to fit a model, which generally is a stump, and every stage we work out which observations aren't classified correctly, and then we form an error weight and work out sort of a confidence in our model. So if our error here is a half, our confidence is 0. And if our error is 0, our confidence is infinity. Okay. And so then we re-weight our observations that aren't classified right. And then we output our weighted majority vote here to the end. And so there are versions of ADA boost or adaptive boosting that work well on the regression problems as well. One unusual feature about ADA boost is that it seems to be fairly resistant to overfitting. So in practice, if you have the more and more models, it seems that it just sort of improves and roughly speaking, it converges with some appropriate rate, and it doesn't start getting worse again on testing data, however many iterations that you take here. In practice, I don't think anyone really quite knows why that's true, but it seems to be true. So, as an alternative then to ADA boost or adaptive boosting, we'll also mention gradient boosting. And that's another form for boosting in some sense. So it was about 1999 that someone realized that you could rewrite adaptive boosting in the same kind of form as gradient boosting. So gradient boosting was actually written down more mathematically around 2000 or 2001 by Friedman. It's a fairly recent implementation. XGBoost, or extended gradient boosting, has won an awful lot of these Kaggle competitions. But it's essentially the same as gradient boosting. So how does gradient boosting work? Well, this is nearly simpler than ADA boost, actually. It's once again a very easy idea. So let's imagine then that we've got some regression problem, and we're trying to predict an output value, yi, for an input vector for features, xi. And we start off by fitting some model, which again is often a decision stump. So it's a really bad model, or a weak learner in textbooks. And then we get some predicted output. Let's say yi0. That's our predicted output for the input variable xi. And of course, it's probably rubbish, right? We're using some fairly bad learning method. So, what's our error term? Well, the error is known as the residuals, epsilon I is 0, and that's the actual output value, yi, minus the predicted output value, yi 0. So here are our error terms. Okay. And now we simply try and fit another decision stump with input xi, and our output now is exactly that error term, epsilon I 0. Okay. So we can see a picture in a minute. Okay. Let's write this down, shall we? Let's use the board. Okay. So, inputs are vectors, say x1, x2, and so on, and the outputs or responses are the values y1, y2, and so on. And we're starting off by choosing a weak learner p0, and then we're defining yi0, say, as the value of our weak learner on the input variable xi. What we hope is that our prediction here is rather similar to the actual output, so we can work out what the error is. Okay, there's our error, and we simply try and fit another tree to the values of epsilon I. Take P1. Okay. And so P1 is epsilon I0 and also an extra error term, epsilon I1. Okay. Well, now we simply substitute this into here. So, epsilon I0 is just the yi minus yi0. So where we get that so yi is the value of P0 plus the value for P1, and also our error term epsilon I1. Okay. And hopefully our error terms are smaller now. And so P0 plus P1 is a better estimate than P0 was. So hopefully errors go down. So P0 plus P1 is a better estimate than P0. Okay. And then we do exactly the same thing. So now we've got some new errors. my new residuals, and we fit a decision stump on our new residuals, and find that the yi is even better approximated, hopefully by p0 plus p1 plus p2, and there's a smaller error here. And so hopefully eventually, when you do this for long enough, we're going to find our actual responses. They're modelled as the sum of lots and lots of decision stumps, p0 plus p1 plus p2 and so on, so long as you like, and there's going to be some smaller and smaller error term. Okay. So here's an example, which again I found online earlier. So let's imagine we've got 5 clusters, and our input variable is just a number from 1 up to 50 here, or 0 up to 50, down there, and their actual values are around about to 10, around about to 20, around about 0, around about 30, and around about to 10 again. And it might be that our first decision stump then is to split around 30, something around there, and then our predicted value on the left-hand side of our split is the mean of all these values, which is, I guess, just over 10. And the predicted value on the right-hand side is the mean of all these values, which is just over 20. And so now we look at our residuals, our error terms, which is how far above and below the red line our terms are. So we're starting off on the red line, and then we're rather above the red line, and then we're below, then we're above, and below again. So we kind of essentially moved our final 2 groups down a bit. After a couple more iterations, it might look something like this. So it looks like we've made